Okay, let's go through the isomorphism theorems for rings. We saw the first isomorphism theorem already, and here is the rest. But I'll take it up from the beginning. This was our master theorem, if you remember. Given three rings, A, B, and C, and two ring homomorphisms, a ring homomorphism F from A to B, and a ring homomorphism G from A to C, that's given, let's say. And suppose I'm told that F is onto, which is denoted like this, onto, and the kernel of F, which is the ideal in A, is a subset of kernel of G. Given this, there exists a unique ring homomorphism H from B to C, such that applying F and then applying H amounts to applying G, which in the picture is denoted like this. And then there is some further elaborations of this. If G is also onto, then H is also onto. If you know that the kernels are actually equal, then this is injective, H is injective. And if you know that the kernels are equal and G is onto, then H is actually an isomorphism. So this hook arrow means injective, right? So if you know both, then you know that this is an isomorphism. That was the master theorem. And this immediately gave you the first isomorphism theorem, which stated the following. Let's say I have a ring homomorphism R to S called psi. Let's say it's onto. Then I could take the kernel of psi. That's the kernel of the horizontal map, call it I. I is the ideal in R, so you have the quotient map from R to R mod I. That's another surjective homomorphism. This is just the quotient map. And the kernel of the quotient homomorphism is also I. So here I have two surjective homomorphisms, phi and psi, and the kernels are equal. So by our master theorem, I know that there is a unique isomorphism here. In particular, R mod the kernel is isomorphic to image. Then you have what is called the correspondence theorem. And this one states, let's say I is an ideal in a ring R. Then there exists a inclusion preserving bijection between the ideals in R mod I and the ideals in R that contain I. There exists an inclusion preserving bijection between ideals in R containing I and ideals in R mod I. And it's a one-to-one correspondence. If you give me an ideal here, I could just take its image in R mod I. That's how this correspondence goes. And if you give me an ideal here, I'll just take its pre-image under the quotient map. where phi from R to R mod I is the quotient map. So what this tells you, maybe I should draw a cartoon. Here is R, and here is R mod I. Here is the ideal I. When you quotient by I and you have this quotient map, remember x goes to x mod I, x plus I. The quotient map. If you take this something in the ideal I, then that goes to 0 in the quotient ring. So this whole ideal collapses to 0. Yes. So you kill the things in the ideal. What this is saying is that you do preserve the structure outside the ideal. If you give me an ideal here, I can take its pre-image and it would give me an ideal containing I. If you give me an ideal here, I can take its image and I'll get an ideal here. And if you give me a bigger ideal K, I'll get a bigger ideal on the right hand side. Yeah, that's the inclusion preserving. That's the correspondence theorem. So when you go to the quotient R mod I, you can forget about the structure inside I and only focus on the structure that is above I, and the ideal structure above I is preserved. Okay. Then you have the, and by the way, instead of ideals, I could have said here subrings. Same statement. Okay. Then we have the second isomorphism theorem. And the setup for that is you have a ring, you have an ideal, so it's an ideal, and you have some subring. Let's put that here. Just a subring. Then you could, on the one hand, consider the, or maybe I call the ideal J for some reason. You could consider the intersection. That's going to be in J, and it's also going to be ideal in S. You can check that. On the other hand, you could consider the sum of these two guys, you know. S plus J. That's a subring that contains J and contains S. So J is now an ideal in S plus J. And then what you have is this quotient is isomorphic to that quotient. So given J an ideal in R and S a subring of R, we have S plus J mod J isomorphic to S mod J intersect S. Okay. And the proof of this, if I can remind you quickly, you have So you don't give the map directly, so you from S you have the inclusion into S plus J, and then the quotient map onto S plus J mod J. And now you look at this composition alpha and verify that the kernel of alpha is the intersection, and then you use the first isomorphism theorem. So S mod S intersection J, you have the quotient map here, and because the kernel of alpha is equal to the kernel of this quotient map, you get isomorphism here. Okay, you have to also check that alpha is onto. That's the second isomorphism theorem. That's a very quick sketch, but you can look up the group theory case. It's exactly the same thing. And then you have the third, finally, isomorphism theorem. It says you have a ring and two ideals, I and J, so that one is contained in another. R is in I is in R, and J is in I. Then you could either quotient out by J first, so you'll get R mod J, I mod J, when you quotient out by I. So this is after quotienting out, and J mod J, which is 0. Then it says that this quotient is equal to that quotient. So given I and J in R, I containing J, we have R mod J mod I mod J, isomorphic to R mod I. Okay. That's also an easy application of the first isomorphism theorem. Okay. Next time we'll try to use the isomorphism theorems to prove the Chinese remainder theorem, so we should see some application.